Hello, Miss Krumzik here again. In this video, I want to show you how to work a more difficult beam problem from the last one that I showed. This one is different from the last one because if you'll notice here at the top, we have a force that's acting in a diagonal direction. And our system for solving beam equations is 3 steps. Step number 1, we need to do the sum of the forces in the x direction are 0. Step number 2, the sum of the forces in the y direction are equal to 0. And then step number 3, we're going to make sure that the sum of the moments about A are equal to 0. That's the 3 equations we need to be considering every single time we look at these beam problems. Sorry, give me a second here to readjust. I always write too big. Okay, so just for a common reference point, notice we have a pinned connection here, and I'm just going to call it A because it's on the left. And this connection over here is a roller, and I'm going to call it B because it's on the right. And we are going to draw in our reaction forces. Remember, if it's pinned, it's going to have a reaction force at A in the x direction, and it's going to have a reaction force at B in the y direction. For my roller here, I am only going to have a reaction force at B in the y direction because it's going to be allowed to expand and contract on this roller. It's going to roll back and forth. Now, the problem here is I have the sum of forces in x and y, but this one doesn't go x or y. It's kind of off to the side. So I want us to remember from our vector component days that this vector is made up of an x vector and a y vector. So we're going to have to find those 2 components, and then that is what I will use as my for my equation for the moments and the forces. So if I want to find the y value here, that is opposite, and I know the hypotenuse. So opposite and hypotenuse is sine. So I'm going to come over here to the side, and I'm going to say the sine of 60 degrees equals my opposite side, which is y, over my hypotenuse, which is 900. So if I do 900 times the sine of 60, then I will know y. So on my calculator, and make sure that you are in degree mode on your calculator because that will change things, and those of you that are in pre-calculus will might have some difficulty. So I found it to be 779.4. And really, I drew my vectors the wrong way. This should go down like this, and my blue should go over like this, because if I start here, I would go down and over. So ignore that. Now it's fixed. Now I'm interested in finding my x direction right here. And so that is the adjacent side to 60, and I know my hypotenuse. So the cosine of 60 equals adjacent, which is x, over hypotenuse, which is 900. So to solve that, I would multiply both sides by 900. So in my calculator, if I do 900 times the cosine of 60, I will get my answer for x, 450. So now I'm ready to begin with my 3-step process. Step 1, the sum of the forces in the x direction have to be 0. So RAX is in the x direction, plus 450 is in the x direction because of this diagonal force, and that has to equal 0. So now my reaction force in the x direction is no longer 0. If I move the 450 over, I get RAX equals negative 450 pounds. So my reaction force here, I assumed it was going in, but it's really not. It's pulling out. It's going to the left. It's negative, and it's 450. Second step in the process is the sum of the forces in the y have to be 0. So I'm starting to look at what vectors are going up and down, and so RBY is going up, minus I have 350 pounds acting down, minus my 779.4 pounds acting down, minus my 775 pounds, and then plus RBY, my reaction force at B in the y direction. So all of those have to equal 0. So I'm going to combine like terms. And I get RBY plus, oh, I'm sorry, this one should be A. My bad. This should be an A. Oops, can't see because of my fingers. This should be an A because of this over here. This right here, and I have an A. That's why I copied it down wrong. Oh, why didn't you guys say something? Oh, it's because I'm in a video, that's why. Okay, just making sure you're paying attention now that I've got you listening again. RAY plus RBY equals negative 1,904. Minus 1,904.4 pounds equals 0. This is as far as I can go with this equation because I have two different variables. So that makes me have to need another equation in order to be able to solve it. And so I'm going to consider my moments. I'm going to start here, negative 450 for RAX times how far away from A it is 0, plus RAY times how far away it is from A is 0, plus I've got negative 350 pounds times 4, because that's how far away it is from A. I have negative 779.4 times 12, because that's how far it is away from A. I have, oops, plus 450 right here for this x, that its perpendicular distance from A is 0, plus negative 775, its distance away is 15. I'm running out of room here. Plus RBY, which is 22 away. All of that has to be 0. So immediately I notice that this is going to be 0, which is very good because I'm running out of space quickly. I have to do 350 times 4, and I get 1,400, negative 1,400. I got 779.4 times 12 is negative 9,352.8. I have positive 450 times 0 is 0. 775 times 15. minus 11,625 plus RBY times 22 equals 0. So now I can combine like terms. I can combine all of these numbers. Negative 1400 minus 9352.8 minus 11,625 is negative 9,492.8 pounds plus RBY, the reaction force at B in the y direction, times 22 equals 0. So I can add this over to the other side. And I'm going to divide by 22. That lets me know that my reaction force at B in the y direction is a 431.5 pounds. So now I can label my reaction force at B. And then I want to go back to this equation right here where I had two variables, and I'm going to work it out down here. The reaction force at A in the y direction plus the reaction force at B, which we just found to be 431.5 pounds, minus 1,904.4 pounds has to equal 0. And I get RAY minus 1,472.92. Oh, I put that as a 1, that's why. Pounds equals 0. And so then when I add that over, I get RAY, the reaction force at A in the y direction, equals 1,473. Let's just go ahead and round that up, pounds. So the reaction force at A in the y direction, 1,473 pounds. So that's how much the bridge is pushing down, and so the reaction back is the same amount so that it can stay stable, remain static. So here are my 3 reaction forces answers. So now we've just solved our second, little more complicated beam problem. Please feel free to go back and watch these examples over and over as you try to work through the problems on your worksheet. Sometimes you need to see something more than once. Feel free to pause and stop, and feel free to skip through my mistakes that I made in this video. I hope you guys have an awesome day of learning, and I will catch you in the next video. Have a good day.